This video will guide you through installing FSL on your machine. I'm assuming you're using a Mac and that for your operating system you have Snow Leopard or later. Go ahead and search for FSL install and click on the first hit that comes up. FSL uses an installation script to set up the program, which you can find by clicking here. Read the license and agree to it, and then fill out the information form about yourself. Then click on Register. This brings up a screen to download the installation script and instructions for how to use it with your operating system. Click on Download FSL and then click on Instructions. We will briefly walk through the rest of the steps, which you can read at your own convenience. Click on this link to install Xquartz, which will download a disk image installer. I already have Xquartz installed, so I'm not going to reinstall it, but the steps for installing it should be the same as with any other package. Once that's done, go back to the installation page. It will tell you to open up a terminal window and then to navigate to the Downloads directory. If you haven't used a terminal before, click on the link in the More Info box below to see an introductory tutorial to Unix. Next, type python fslinstaller.py and then press Enter. This will start the FSL download and installation. There are a couple of steps that will require you to enter your password to proceed, so you will need to stick around for the entire installation. The defaults are fine as is. Unless you are an advanced user, there's no need to change them. The installation will take about 10 to 15 minutes. Once the installation is done, open up a new terminal and exit out of the old terminal by typing exit. Test your installation by typing echo $FSLDIR to see that the path is set correctly. If you selected the defaults, it should point to user local FSL. Next, type flirt-version to make sure that the commands are working. It should return version 6.0. Type FSL from the command line to make sure the FSL windows open correctly. Lastly, type FSLize from the command line to open up Fossilize, the FSL image viewer. If all of these run without any errors, you've successfully installed FSL and are now ready to use it. If you need to install patches or updates, or if you run into any errors in the installation, check the installation page. Or, if you're having trouble with Fossilize, look at this page by searching for Fossilize Troubleshooting. This is an introduction to FSL, the interface, and just a brief overview of the fundamentals of starting up FSL and looking through some of the different tools that are available. Now, if you've had experience with, say, another fMRI analysis package like AFNI, SPM, or Brain Voyager, the concepts are the same, but the execution is slightly different. So before we get started, we are just going to look at the FSL interface right here. When we bring this up, we see a list of different tools that FSL has available, such as brain extraction, segmentation of gray matter, white matter, and cerebrospinal fluid, independent components analysis, and looking at images through FSL View. Before we get into more about the graphical user interface, I also want to point out that many of the tools can be driven from the command line. For example, if we wanted to use FSL View, we could simply go to our terminal and type in FSL View. This will bring up the FSL viewer. If we want to open up an image, all we need to do is go to File, Open, and then select one of our functional runs. This looks like a typical fMRI dataset, and we can see it has relatively low spatial resolution, but that you can still see important anatomical landmarks such as ventricles and the major gyri and sulci. I'm also going to go ahead here and open up an anatomical data set. This is the brain of a highly intelligent long-distance runner that we scanned a few weeks ago. Within FSL View, you might notice that the orientation in some of the window panes, like right here, looks a little bit odd. However, the important thing to notice in FSL View is these markers at the sides here. For example, R and L stand for right and left, and S and I stand for superior and inferior. In this case, it's perfectly reasonable that this could be the right side of the brain and this could be the left side of the brain. If, however, the labels here were S and I, that would imply that there's some sort of error with either the header information or the way the image came off the scanner. Going back to the FSL interface, although we have several different tools at our disposal, the two most important ones for the beginner with FSL are BET and FEAT. Let's start out with BET. BET stands for Brain Extraction Tool. And what this will do is remove skull and meninges from an anatomical data set. We'll be using this at a later stage during the FEAT analysis. All that's required is an input anatomical data set. Here it's S007A1001. And as you can see, it automatically fills in the output image that it wants to export. All it is the name of the image that I put in the input with _brain appended to it. Most of the rest of these defaults work just fine, although if you wish to go into them in greater detail, you can mess around with them or look on the FSL website. Once we're done specifying our input and output images, all we need to do is hit go. This illustrates a very important concept of FSL. Whenever you use a tool from the FSL GUI, it also outputs what will be run from the command line. For example, if I want to go back and just run this output code right here, I can just copy and paste it into my terminal and then run it without having to go through the FSL GUI. Now that we're finished, we've output an image that is stripped of all skull and meninges. Clicking on FSL View here will bring up the same FSL View tool that we looked at previously. As we can see, BET did a relatively good job of extracting the brain from surrounding tissues. This illustrates an important concept of all fMRI data analysis. Look at your data after each processing step or any time you apply a transformation to your data to make sure that it looks reasonable. If it doesn't, go back and look at the error logs to see what might have gone wrong. Lastly, we're going to do a very brief tour of the FEAT interface. FEAT stands for fMRI Expert Analysis Tool. FSL is really big on acronyms for some reason. As you can see, FEAT goes through the processing stream linearly. So for example, if you want to do a full analysis, you'll start with data, then do pre-stats, then stats, then post-stats, and finally registration and normalization. Also notice these two drop-down menus here. You can do a first level analysis or a higher level analysis. Just to be clear, with FSL, a first level analysis typically refers to analyzing a single run of data. This is opposed to the usage in, say, SPM or AFNI, where a first level analysis refers to doing an analysis for an entire single subject. A higher level analysis then might mean combining first level analyses or runs across a single subject. And then another level above that would be combining data across subjects to perform a group level analysis. This other drop-down window here allows you to specify only certain subsets of the analysis stream. For example, you might only be interested in doing pre-stats for a certain subject, or let's say just interested in doing registration. When you do this, the parts of the processing stream that are not selected will be grayed out and you can't select them. Now let's look briefly over the rest of the tabs. In Data, we can select all of our different 4D functional data sets, as well as any output directories we want to export them to. Also notice that whenever we hover over any of these fields, we get a help bubble that appears after a few seconds. Prestats allows the specification of different pre-processing steps such as motion correction, field map unwarping, slice timing correction, and smoothing. The Stats tab of feet is probably the most involved part of the analysis stream. We'll talk more about this later, but it involves your model setup to try to model the time series that's going on in each voxel in your data. Post-stats allows you to threshold what clusters of activation you see on the final images after they've been processed and had a model fitted to them. Lastly, registration is done to co-register your functional images to an anatomical dataset, warp the anatomical dataset to a standardized space, and then apply those transformations to the functional datasets. After you're done with all of these different parts of your analysis, all you do is hit Go to run the feet analysis. Alternatively, you can hit Save, which will output a file called design.fsf. You can then use this to batch your analyses, which can make it much faster. We'll also be talking more about this at a later time when we discuss more advanced uses of FSL. That's it for this brief overview, and in the next tutorial we'll be talking more about the initial stages of setting up a feet analysis.